Okay, cool. So we're recording. Yeah, so you're going to be starting your master's. And, you know, I'm working on my master's in computer science. And so I figured today we could start by just going over what I'm working on, because I don't think that you need kind of the more introductory math to start. So linear algebra is the course that I'm taking. And it's all about systems of equations, kind of like when you were in like regular algebra, right? And we learned about maybe like y. One moment. So we had like y equals 2x plus 1. And then we had like another equation would be like y equals 3x minus 2. Right? So how would you go about solving this? Right? And first how would you know that you could solve it? And how would you solve it?
Well, I think you'd start with at least an easy place to start is where the y-intercept is going to be. So right with the first one up there, if it's plus 1 at the end, there's going to be a point at 0, 1 on the graph.
Okay.
And then the 2x means you're going to be going essentially 2 to the right every time you go 1 up. So we'd have a point at what, 3, 3, 2, and so on.
So y1 at 0 equals 1, right? y1 at 1 equals 2 times 1 plus 1 equals 3. So then we have 1, 2, 3 here. And then, so you're thinking about this from like a graphical point of view.
Yeah.
Okay. Go back. And then you would graph the other one, would be negative 2 here, and then over 1 up 3, 1, 2, 3 would be here, and you do something like that. And maybe like if we had like graphing paper, this would be like a little clearer.
Sure,
right? Yeah. So what I would do is I would say, okay, well, you're saying like where do these points cross? And I'd say these points would cross where the x's and the y's are the same, right? And so one thing we could do is say like, okay, well, if y1 needs to be equal to y2, we know that y1 is 2x plus 1, and y2 is 3x minus 2, right? So where the y's are the same, these are the values that the x's need to be, right? And so then we could say, okay, well, if we subtract the 3x from here, we'd have negative x. Okay. And then subtract the 1 from over here is negative 3, right? And then x would be equal to 3. And any equation we could plug it into, let's say like y1, where x is 3, would be 2 times 3 plus 1 equals 6 plus 1 equals 7. And we could do the other equation, would be y2 at 3 equals 3 times 3 minus 2 equals 9 minus 2 also equals 7. Right? So where these two lines cross is at the point 3, 7. And this is the solution, we'd say, to this system of equations. And you may have gone as far as to say, make sure I got this working here. Okay. We may have also gone as far as to say, maybe you had like 3 variables, right? And if you had 3 variables, like let's say like x plus y plus z equals 1, do you know like how many equations we would need to figure this out?
No.
Okay. So if I have 3 unknowns, so 3 variables, x, y, and z, then I need 3 equations in order to have enough information to figure out like what the solution is, right? So if I have only 2 equations, like 2x plus 2y equals 8. I'm just making numbers up here. Well, then I would have no way of figuring out where this all works, right? Because if I, let's say, okay, well, cool, like, because the solution that we would do would be, I'm going to try to get, one side to just be one variable, and then the other side of the equation to be, either a constant or just all of the other variables, right? That's kind of like the way we would go about it. And so then we would say, like, okay, 2x equals 8 minus 2y, right? And then x would be equal to 4 minus y, which could be fine if we had enough equations, but I'll just kind of show you what happens, right? So now we're going to substitute x in here, right? And we end up getting 4 minus y, that was our value x here, right? Plus y plus z equals 1. And in this case, it does work out. But like, let's just say I made this 2y, right? Just because I'm trying to be illustrative here, right? So in this case, before I kind of fixed it up here, we had 4 minus y plus z equals 1, and then we could say z equals negative 3, right? And then I would know that z is equal to negative 3, right? Which is cool. In this system, I can always know what z is. But if I go back and I try to figure out what x and y are, like, there's nothing left for me to do, right? Like, I know that x is 4 minus y. I know y is x minus 4, right? Because I could just do it this way as well. I can also say it's the same thing as saying that, or y equals 4 minus x, right? If I add y and then subtract x. But there's nothing left for me to do here because z is negative 3, but I can't plug it in. So the solution to this system would be a set of things that we know and a set of things that are kind of things we don't know, right? We can't like have a full solution. Some systems we could have full solutions, and you can kind of guarantee to have a full solution without any variables in it if you have the same number of equations as like free variables, right? But in this case, we could also have, like, if I changed it to 2, and I made this, let's go down here, and let's just pretend that I made this 2y, right, plus z equals 1. Okay. Now, if I do this and I simplify it, I don't really have any more information, right? I just kind of, now I have this new equation, which is cool, and I have this old equation, which is cool, but I haven't really figured anything out. And the problem here is that we have 3 variables and 2 equations. So there's no like guarantee that I'm going to get any more information. So linear algebra is kind of, as far as I can tell, like the next, so far that I've learned, it's kind of like taking this idea of, I have a bunch of equations, and I'm going to get, the previous way we learned about it is, okay, I'm going to get everything else on one side and x on one side.
Yeah.
And then I'm going to substitute it all in. And then I'm going to use the next equation, right? If we had a third equation from here, I could plug in, z, and I could plug in x, and then I could eventually get like 3 solutions.
Yeah.
Right? So for linear algebra, we're basically doing that, right? So let me find a practice problem. So yeah, so now we're talking about these like systems of linear equations is basically what we're going to go into. Okay, so let's just take this one because it's kind of easy. So on one side, and I'm just going to write it down here before I switch screens so that I have it all. I'm going to save all this off. Okay. So we have w plus x plus y plus z equals 6. And, oh, I see. So this is kind of like a more complicated. So let's do number 3 first, because there's 3 and 3. That'll be a little easier. Okay. So this one is x plus y plus z equals 2. And then we have x plus 3y plus 3z equals 0. And we have x plus 3y plus 6z equals 0. And let's solve it kind of the way that we're more familiar with first, and then I'll kind of go into some more complicated stuff. Right? So what would be, like, if you were going to solve this, what would be your first step?
I would probably, I don't know, which one would we isolate first?
Probably either x, y, or z in the first row, I think would be the easiest. They're all simplify pretty much the same. So let's just pick x. All right. So we have x equals 2 minus y minus z, right? Now I'm going to pick x, and I'm going to substitute it in here. And I get 2y minus z, 2 minus y minus z, plus 3y, plus 3z equals 0. And then I'll simplify this a little bit. So we have 3y minus y is 2y. We have 2 plus 2y here. And then we have 3 minus z is plus 2z equals 0. Okay, so now we have one equation, right? That's kind of a mixture of 2 equations. And we need another equation that isolates either y or z so that we can get a solution for y or z. So we have to use this one, right? So let's just say, let's do y. So this would be y equals 6z minus x over 3, right? And then we have 2 plus 2 times 6z minus x over 3 plus 2z equals 0. Okay. 2 plus, this is 2z times 2 is 4z, right? 2 times 6 divided by 3 is 4. Minus 2/3 x plus 2z equals 0. Oh, what did I do wrong here? Oh, and then we substitute in x, right? I did something wrong. Let me go back a little. Okay. So we have x equals 2 minus y minus z, right? I think this is where I went wrong. I think we need to substitute x into both equations first. So, this is getting a little confusing, all right? So this would be, let's call this like equation A and B and C. All right, so A turns into, or sorry, A is this one, right? So B becomes 2 minus y minus z equals, 2 minus y minus z plus 3y plus 3z equals 0. This is 2 plus 2y plus 2z equals 0. And then we can divide everything by 2, and we get 1 plus y plus z equals 0. And then equation C, we plug it in, and we get 2 minus y minus z plus 3y plus 6z equals 0. Now we have 2 plus 2y plus 5z equals 0. Okay, so this is, I think this is what I did wrong. So we went from 3 equations and 3 unknowns to 2 equations and 2 unknowns, right? Now we're going to go to 1 equation, 1 unknown, solve it, and then plug our way back up, okay? So the easiest one would be this guy here. So let's say z equals negative y minus 1, right? So if z is negative y minus 1, then we can plug z in here and get 2 plus 2y plus 5 times negative y minus 1 equals 0. So that's 2 plus 2y minus 5 y minus 5 equals 0. And then we can simplify 2 minus 5 is negative 3. 2y minus 5y is negative 3y equals 0. Then we can add 3y to each side, so then we get 3y equals negative 3, right?
Yeah.
And then y equals negative 1, and then we can plug this back up. Z equals negative y times negative 1 minus 1 equals negative 1 times negative 1 is 1 minus 1 equals 0. And then x is 2 minus negative 1 minus 0 equals 2 plus 1 equals 3, right? And then we could say 3 plus negative 1 plus 0 equals 2. We checked it, and we could check the rest of them. Okay, so that would be like our, the way that we would solve it before. Took me a second to get there, because I haven't done that in a while. Alright. Alright, so how would we do this like the linear algebra way? Alright. So we go back and we say x plus y plus z equals 2. X plus 3y plus 3z equals 0. X plus 3y plus 6z equals 0. Alright, so in linear algebra, we're gonna kind of think of things a little bit differently, and we're gonna do some operations with matrices. Have you ever worked with like vectors or matrices before in school?
Not that I recall.
Okay. So the way we write it would be, okay, we're gonna say in matrices and vectors we have like rows by columns. Alright? So in this case we would have the first row is like this first equation, right? And each column represents some variable, right? So the first column represents x, the second column represents y, and the third column represents z. And then we're actually going to add a fourth column that represents the equal side.
Okay.
Okay. So the number in every entry, right, is the coefficient of the variable. So here we have, in the first row is 1, 1, 1, and then 2. And in the second row, we have 1, 3, 3, 0. In the third row, we have 1, 3, 6, 0. And what I've seen, and so to kind of represent this, usually we have like brackets here. So when you see like brackets, we're talking about matrices. Yeah. And then sometimes what I've seen professors do is kind of do a dotted line here, just to remind ourselves that the stuff that's on the right side of the dotted line is the right side of the equation, and everything else is the left side of the equation. And when we write a matrix like this is called the augmented matrix. The augmented matrix just means that we've added this extra column to represent the right side. And then we would call this a 3 by 4 matrix, because it has 3 rows. Row 1, row 2, and row 3. And it has 3 columns. C1, or 4 columns, sorry. C1, 2, 3, and 4. Everything makes sense so far?
Yeah.
Okay, cool. So linear algebra is like all about this stuff so far that I've done. So everything is like matrix and vectors. Vector just means, like, did you take like physics in school?
I did, yeah. It was a while ago.
Yeah. So a vector just means, like, in math, you're usually talking about things in terms of just like sheer magnitude.
Yeah.
A vector represents some magnitude, so some like number, some scale of something, but also a direction. So if we just had like xy, right? And then we had a line, just like a very simple line. So like 1, 1. Alright, so y equals x. You can represent this line as a combination of vectors, right? So, or let's say like you could represent this point on the line as a combination of 2 vectors. So one vector is the vector, let me make sure I get this right. I think it's written like this. It would be like 0, 1, right? So and then it would be plus 1, 0. And it's essentially saying, oh, you can imagine like we have like a mini arrow down here. Maybe better would be to show it up here. We have like one arrow here and one arrow here, right? Kind of like when you were in physics and we talked about if you throw a ball, right? And you throw a ball over here to this other guy. And the ball moves like this, right? And you have a bunch of forces acting on the ball, right? You have the force of the person throwing it, but then you also have the force of gravity, right? And the path of the ball is affected by both of the forces, right? Like it's not going straight over, and it's not going straight down. It's kind of going both directions, right? And also, like, there's a force up, right? So the guy throws the ball up and over, and there's a force of gravity. So the ball is moving and moving and moving, and then gravity affects it more and more and more, and it kind of comes down, and then the person catches it. So that's what vectors are all about. It's about kind of directions of different magnitudes. All right. So to solve this system, we do something called row operations. So we have 1, 1, 1, 2. I'll show this. Okay, yeah, it's coming up pretty quick, pretty good. 1, 0, 0, 1, 3, 3, 0, 1, 3, 6, 0. All right. So what we're going to do is we're allowed to do, in matrix land, we can kind of do similar stuff that we can do in like regular algebra land. So the things that we're allowed to do are called row operations. And there are 3 different row operations that we can do. One row operation is that we can switch rows. And this should make intuitive sense back from here, because the order of the rows didn't really matter, right? Like the order of the equations. Like if we started with these 2 equations, and then we replaced them into the other 2 equations, like it didn't really matter which way we did it, right? Like if we went back and isolated x with the 3rd row and then replaced it into the first 2, we would have come to the same conclusion, right?
Yeah.
Yeah. So what this says here is that the rows don't really matter, like which rows are in which position. What really matters is what are the coefficients of the rows and how do they match up to the right-hand side, right? That's what matters. Like if you started switching the coefficients over here, and you made the top row, you know, if you switched like y and 3y, right, and you made it x plus 3y plus z equals 2, like that would totally mess things up.
Mm-hmm.
Yeah. So you're not allowed to switch columns, but you are allowed to switch rows. And it can be convenient to do that. So that's kind of like the simplest thing you can do. Okay. The second simplest thing that you can do is you can multiply every number in the row by some constant, some non-zero constant, right? So what you can do is you can say a, which is like a is like anything, some non-zero constant. A, Ri, and Ri by I just mean like any row, it doesn't matter. And then you can replace that with the same row. So this notation just means like if I wanted to multiply the first row here, and this isn't really like effective, but just to kind of demonstrate, I could multiply the first row by 2, right? So I could say 2 times Ri going into Ri. And what this would do is it would give me 2, 2, 2, 4. And sometimes this is useful. Usually we're doing it like dividing by 2, multiplying by a half is more typical what we would do. And this should make sense, right? Because if we go back to the equation here, it's the same as multiplying 2 on each side of the equation, which we're totally free to do that, right?
Yep.
Makes sense?
Mm-hmm.
Okay. Now, the more complicated thing that we can do, which is essentially doing the same thing as isolating the variable on one side. Kind of another way that we can solve the equation is we can subtract 2 rows, and that's another way of like reducing our equations, right? So like another thing that we could do. So another thing we could do is, like, let's say I had like x plus 3y equals 2. And then I had like 2x minus 3y equals 5. Right? Like one thing, we can definitely still do it this way, right? We can still say like x equals 2 minus 3y and then substitute it in, right? We could do that. But a more easy way of doing it is we can just kind of like add these 2 rows, and then we could say like 3x plus 0y equals 7, and then x equals 7 over 3.
Yeah.
Yeah. So that idea, we can do the same with matrices. And that's our third thing we can do, the third row operation. And that is I can add Ri, so some row to another row to replace in another row. And the reason we would want to do that is to get 0 in one of the entries here. Right? So our goal, like what's our goal? Our goal, like the ideal thing that we could get, right, would be something like this. This would be the ideal. 1, 0, 0, 3, 0, 1, 0, 4, 0, 0, 1, 5. This is the absolute ideal. Because if we think of this back as an equation, right, we have x equals plus 0, right? So x plus 0y plus 0z equals 3 my iPad is glitching a little, 1 second. Okay. And then y equals 4, z equals 5. Right? This is like solved.
Yeah.
The like second best thing that we could do is pretty close. It would be something like 1, 2, 3, 4, 0, 1, 5, 6, 0, 1, oh sorry, 0, 0, 1, 7, right? And you'll notice the theme here is kind of this staircase looking thing. And this represents, you know, x plus 2y plus 3z equals 4, y plus 5z equals 6, and z equals 7, right? And then it's pretty simple from here, right? Like I can just plug z here, and I can plug y and z here, and then I get it, right? So like this is like good enough, good enough. And so we call, when it's in this like zigzaggy form, it's called echelon. And I don't know, probably some guy. I don't really know. But we call it echelon form. Okay. And so the goal is, let's do these 3 row operations to get it in echelon form. And if we can get it here in the staircasey view, even if not everything is 0, like it's kind of trivial to solve it from there. Like all somebody has to do is plug it in, right? There's not really a lot of thought that has to go into it. Okay. So let's do an example. Let's do the same example, but let's try with row operations. Okay. So let's start fresh. All right, we have 1, 1, 1, 1, 1, 2, 1, 3, 3, 0, 1, 3, 6, 0. Okay. Let me make this a little smaller. Okay. So we have 1 in the top left already. So there's not really much to do here, right? The goal would be, we want 0 on here and 0 on here. And then we'll start working to get like 1 here and 1 here. Does that make sense?
Yeah.
Okay. So I'll give you the first example. So let's do R1 plus negative R2. You could also think about it as minuses, but I find that there's going to be a lot of like mental math here. And so keeping it like plus negative for me helps keep me from getting confused. Because there's a lot of like 1 times 2 minus 3 equals this and that and the other thing, right?
Yeah.
So that's my advice. So if we do this, we can say, okay, I think maybe better would be to write it as R2 plus negative R1 equals R2. All right. So 1 plus 1 times negative 1 is 0. That's why we chose it, right? So what I'm saying is we're going to take this number, is R2, and we're going to multiply it by, we're going to add it to negative 1 times this number. And that's going to be 1 minus 1 equals 0. Does that make sense?
Yeah.
All right. And then we'll write it up here. We have same top row. We didn't do anything to the top row. We're replacing the second row. So that's how we got a 0 in the front. Right? So that's the goal, which is why we chose to add negative R1 to R2 to get 0 in the front. Okay? But now we got to fill out the rest of the row. So 3 plus negative 1 times 1 equals 2. Okay? So we get 2 here. And then 3 plus negative 1 is 2. And 0 plus negative 2 is negative 2. Cool?
Mm-hmm.
All right. So we also want to get 0 here, right? So how would we do that?
Would you mind zooming in a tiny bit?
Yeah, totally.
You're going to have to walk me through it.
No problem. There's a lot of like, how did I get here, right? So we got 0 here before, right? Because we basically want to subtract. So this, remember, let's take this 1330 and let's write it out like we're used to. Okay, so that's like x plus 3y plus 3z equals 0, right? And let's take the first row and we'll write it, because remember we said that we can interchange the rows. It kind of doesn't matter, right? X plus y plus z equals 2. Are you with me? Okay. And I told you that we could subtract or add rows, right? So we know that we can do something like this, right?
Yeah.
Where these cancel, and then this is 2y plus 2z equals negative 2, right?
Yep.
So that's how I got 2, negative 2. So 0x plus 2y plus 2z equals negative 2. Okay, that's where this came from. And so, because I don't want to write out x and y and z every time, what you end up doing is a lot of mental math to essentially do what we did here, but just like in your head, right?
Yeah.
So we write that as this is R2, and this is R1, right? And then this becomes R2 again, right? And that's this. Okay? R2 plus negative 1 or minus R1 goes into R2. And then we have a new equation where there's no x, because that was the goal. We have x in the first equation, the first row. We want no x in any other row. We want zeros for x, right?
Gotcha.
Okay. So now we want zeros for x in the third row, the third equation, right? And we can use the first row again. We can do the same thing, but just with row 1 and row 3. So what do you think that we should do? Like, how would you write this thing here?
You probably want to subtract. I mean, would you subtract?
So this is R1.
You start with R3, right?
Exactly.
And then
So we
you
would do
subtract,
R3.
probably subtract R1 from it.
Yes. Yep, that's it.
Yeah, makes sense.
Okay. So we're gonna keep going. So we're gonna send this over here, right?
Yeah.
So we didn't change anything about, right? So this equation doesn't, this operation here, it doesn't change anything about R1 and R2.
Yeah, okay.
It just changed what's in R3, right? So when we write our next thing, we can already fill in what everything else is, what the first 2 rows are.
Okay.
Because we didn't do anything different. We're just trying to figure out what's the new R3. Right?
Yeah.
Now we know that the first is a 0, right? Like we
Sure,
We
yeah,
chose
1
it
minus 1.
for this specific reason. Right? So then the question becomes, well, what are the other two going to be? So if we subtract 3 minus 1, we get 2, right?
Mm-hmm.
What's the other one?
It'd be 5. 6 minus 1.
Mm-hmm. And then the last column would be...
Is that a 2 in row 1?
That's
0 minus 2?
Yes. So
Right, so
negative
we'd
2.
have negative 2.
Yep. Exactly.
Okay, I see.
Mm-hmm.
And now we could use the new rows 2 and 3.
Yeah, yeah.
You end up with 0. I got you.
Yeah, so the next thing is we want, so the two things that we got to do left, right, we're very close to the zigzag. You know, I'd say we're halfway there. What we need is 1 in, like, for every row, the, like, column that corresponds to the row. So, like, the first column in the first row, and the second column in the second row, and the third column in the third row, they all start with 1, and there's zeros everything before it. That's when we're, like, done, right? So there's two options, right? So we know we have to get 1 here.
Yep.
And we know we have to get 1 here. And we know that we have to get 0 here, right? But the order in which we do that doesn't really matter, okay? So I would suggest, since this is just like our first exercise, I'm just going to like tell you what to do, right? I would suggest we do kind of the same thing. So we do we want 0 here, right? So we want R3 minus R2, or, you know, plus negative R2, doesn't matter, into R3, so that we end up getting that 0 here.
Yeah.
Okay. So, again, we can kind of write out the first two rows, because we're not changing them in this operation. And we specifically designed this so that the first two would be zeros. And then we just got to figure out what are the last two columns.
We have 3 and negative 4, right?
Yes. Well, this would be 3 is correct.
Oh, sorry, minus negative 2.
Yeah. So this is where you have to be careful.
Yeah.
And this is why I was suggesting the, like, plus. Because when you're always adding, the double negatives are front in mind, right? Yeah. So but yeah, we got here, right? Okay. So perfect. We're like halfway there. We have the, like, zigzaggy staircase, but we need to get it reduced so that there's only 1 in that slot, right? So we can go back to our equations, right? And I told you that we can multiply or divide the entire row by any constant that's not 0, right? Obviously, you can't just, like, multiplying everything by 0 on both sides. You're just going to get 0 equals 0. It's not going to be helpful, right? So now all we need to do is divide the second row by 2 and the third row by 3, and then we're done. Right? So what would that be? Oop.
We'd have, for the second row, we'd have 0, 1, 1, negative 1.
Yep. And then
we'd have 0, 0, 1, 0.
Exactly. Okay.
Yeah. Okay.
And if we plug this back into what we're familiar with, we'd have z equals 0. We'd have y plus z equals negative 1, which implies that y plus 0 equals negative 1, or y equals 0, or y equals negative 1. Okay. And then we'd have x plus y plus z equals 2. We know that z is 0. X plus negative 1 plus 0 equals 2. And we know x is equal to 3. Which, if we go back to wherever we were solving this before, I forget. Yeah, so we got 3, -1 and 0 back here. It's the same, and what's nice about this is it's very easy to check, right? You got 3 equations you can check, right? So, you know, like, let's just pick one of these. Let's just pick one of these. You know, and what's also nice is that all of the equations you can check with all of them. So every single row you can use to kind of validate your work. So we had like x plus y plus z. Let's use the third one. We had x plus 3y plus 6z equals 0. And we said that x is 3 and y is -1 and z is 0. So 3 minus 3 plus 0 equals 0. 0 equals 0. Looks good to me.
Mm-hmm.
Everything clear so far?
Sure, yeah.
Yeah, okay, cool. So, let's use another example. Okay. Let's do this one. So we have x plus y plus z equals 6, and x plus 2y plus 2z equals 11. And we have 2x plus 3y minus 4z equals 3. Alright. And let's make this smaller. Maybe that's too small. Okay. Alright. My additions got kind of messed up here.
That's weird.
Yeah, I think my Apple Pencil is running out of battery, or something like that. I'm not 100% sure. So let's start with writing the augmented matrix. So what would that be?
So row 1, we'd want to go 1, 1, 1, -6.
Yep.
Row 2, 1, 2, 2, 11.
Yep.
Is that an 11? Okay.
Yeah, it's 11.
And then row 3, 2, 3, -4, +3.
That's right. Okay. So as you do more of these, you're gonna catch things that will make it a little easier for you.
Yeah.
So, what I would suggest is, like, what really stinks when you're doing this is dividing, like, having fractions. Alright, so when you start working with, like, 1/2 or, like, 2/3, like, it gets confusing. Easier to work with whole numbers, right? And when you have a bunch of positive numbers, it's easier to think about it in terms of, like, subtracting. So my recommendation is, even though we have the 1 here, well, I guess there's 2 things you could do, right? One thing you could do is switch this row and then like multiply everything by 2 and subtract. But now that I'm thinking about it a little bit more, I think it's not really necessary, because you can multiply either one. You can multiply the thing that you're starting with, or you can multiply the row that you're subtracting or adding, so it doesn't really matter. So remember that the goal is to get a 1 here, and a 1 here, and a 1 here. Right? So we already have the 1 in the beginning, so what would you suggest that we do next?
We probably want to maybe subtract row 2 from row 3 to get that 1 in row 2. I don't know.
So we want it to look like this. Where we have 1 here, 1 here, 1 here, 0 here, 0 here, 0 here. Alright, so we already have, I recommend getting the zeros in place before you try to get the ones in place. Like, if you don't have a 0 leading the row, don't worry about trying to get a 1 in the position that it's supposed to be. Because you're probably going to have to do it again. Because you're going to be adding stuff. Right? So how would we get, if the goal is to get a 0 in the first position on the second row, right? And a 0 in the first position of the third row, how would we do that?
We'd have to do subtraction, but for the second row, subtract. You'd be subtracting row 1 from row 2, right?
Yeah, exactly. So we're going to do row 2 minus row 1 into row 2. Right?
Cool, yeah.
Cool. So we didn't do anything in row 1. We put a 0 here.
Yep.
We didn't do anything to row 3. So if we subtracted the other ones, what would we get?
We'd have 2 minus 1.
Yep.
So we'd have a 1 right there.
That's right.
And the same thing. And then 11 minus negative 6. So we'd have 17 there.
Yes. Exactly. Now we're doing pretty good. Right? So the things that we still need to take care of are we need to get zeros in, like we need to fill the zeros in on the third row. So what we can do, I'll give you the first one. Right? So we could do row 3. We're going from row 3 to row 3. Right? So this is kind of the template, right? Row 2 to row 2. Row 3 to row 3. And then we're going to add or subtract another row. Okay? In this case, we have a 2 in the front of this one, right? And we want to get it to 0. But we're only working with 1 up top. So we can multiply row 1 by 2 so that we just do 2 times R1. And that's fine. Because we can multiply an entire row by any constant and it doesn't change what it means. Great. Cool. So that's right. So then we would have the same top. Nothing has changed in row 2. And then we said that this was going to be 0. Right? So what are the other ones? It would be
3 minus 2.
It would be exactly 3 minus 2. So 3 minus 2 times 1. So 3 minus 2 is 1.
And we got negative 4. Sorry, what?
No, yeah, go ahead. That's good.
And then negative 4 minus 2 times 1.
Yep.
So we'd have negative 6 there.
That's right.
And then 3 minus negative 12. We'd have negative 15. Sorry. I went backwards. Sorry.
Yeah. So it would be 3 just for whoever might be watching. It would be, and this is like you get better at this as you do it, but it's very, 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 very easy to make a mistake.
Yeah.
So 3, especially when you're doing the double negatives. So 3 minus 2 times negative 6 is 3 plus 12 is 15. Maybe that's what you said.
No, I said negative 15. I flipped it in my brain.
All good. Okay. Now we're very close, right? What's the next thing that we should do?
We'd have to turn that negative 6 into a 1, right?
We do have to do that, but remember, I suggest we get our zeros out of the way.
Okay.
Yeah, because once we get the zeros in there, then we can kind of scale the rows, and it doesn't really matter. But it's really the zeros that's like solving the equation. The scaling is just kind of for convenience. The goal is to get it such that we have one variable in the last row, then 2 variables in the second to last row.
Yeah.
And then, right, and so in this case we're just doing 3, but like, we could do this this exact same thing for 50 by 50.
Yeah.
For 1,000 by 1,000, which is like essentially what is actually useful in real life. But that would be super hard to do on paper, right? So usually in school we just do like 3 or 5 or something like that. Okay.
You get the one step down.
Yeah, exactly. And then you just program a computer to do it.
Yeah.
Okay, so the goal is to get a 0. So how would we do that?
We'd want to subtract probably row 2 from row 3, right?
Yeah. So we would do row 3 minus row 2 into row 3. Alright, and then
we'd have a 0, and then we'd have our negative 7.
Yeah.
Or sorry.
No. You got it.
Okay.
Negative 6 minus 1 is negative 7. You're bad at mistake. Alright? And then what?
15 minus 6, so we'd have 9 there. Sorry, I did it again. Minus negative 6. So we'd have 21.
So we're doing row 3 here minus row 2. So it would be 15 minus 17. It would be negative 2. Okay. And now we can do the scaling to get the ones. So the first 2 are all set, so we just need to scale the second one. Alright. So we could just do multiplying the entire row 3 by negative 1/7. And then we would get negative 2 divided by negative 7 would be 2 over 7. Looks like it to me. I'm a little suspicious that we made a mistake because we have weird numbers. Very easy to make a mistake. The best part, though, is we can always check. So we can get to the end and know that we made a mistake and then go back and fix it. Right? So let's figure out what we got going on here. So that means z equals 2 over 7. Right? And we have y plus z equals 17. So that would mean y equals, gosh, I don't know what 17 times 7 is. I'm very suspicious. Let's just do 17 minus 2 over 7. And yeah, so let me check our work, because I'm suspicious, right? So we did R2 minus R1 into R2. So we did 1 minus 1 is 0. 2 minus 1 is 1. 2 minus 1 is 1. And 11 minus negative 6 is 11, plus 6 is 17. That looks good to me. And then we did 2 minus 2 times 1 is 0. And we did 3 minus 2 times 1 is 1. Here. And then we did negative 4 minus 2 times 1 is negative 6. And then we did 3 minus 2 times, this is where we were wrong, right? I made a mistake here. But it's recoverable. We did, so the last two are negative 4 minus 2 times 1 is negative 6. That looks good. But we need to do 3 minus 2 times 17. 3 minus 20 plus 14 is 34 equals negative 31. Okay. So that's 1, 1, 1, negative 6, 0, 1, 1, 17, and then 0, 1, negative 6, negative 31. Does that seem right to you?
I couldn't tell you. I don't know. I don't understand the mistake still.
Okay. Well, let me try to explain it and make sure it is a mistake.
Okay.
So I'm talking about this operation, right? We did 2 minus 2 times 1 is 0, right? So we did 2. Oh, that could be confusing. We did 2 times 2 minus 2 times 1 is 0.
Yep.
3 minus 2 times 1 is 1. Okay? We did negative 4 minus 2 times... Oh! I'm getting confused again. Let me get rid of this. Because maybe it was a mistake. Alright, so...
Yeah, but it seems right. I don't know.
1, 1, negative 6, 0, 1, 1, 17. And then we did 0. We said this was 1. We said this was negative 6. And then we did 3 minus 2 times. Oh, yeah. Maybe we were right the whole time.
Yeah, 15, right?
Yeah. 3 plus 12 is 15. Okay, so maybe that wasn't it. Or maybe it just has like a weird solution.
Maybe, yeah.
I suppose.
Yeah.
Alright. Let's go back and see if we can figure it out. Alright, so this is 15. Okay. Now this is going to go to 1, 1, 1, negative 6, 0, 1, 1, 17. And then 0, 0. Negative 6 minus 1 is negative 7. And 15 minus 17 is negative 2. Yeah, alright. Well, let's plug it in and see if that makes any sense. And if not, then, you know, I guess I'm taking this class too. So. Alright, so we got z equals 2 over 7. And we have y equals 17 minus 2 over 7. And we have x plus y plus z equals negative 6. So x plus 17 minus 2 over 7 plus 2 over 7 equals negative 6. And we have x, these cancel, plus 17 equals negative 6. And we have x equals negative 23. So our solution is negative 23. I don't know what 17 minus 2 over 7 is, so I'm just going to write it as this. And 2 over 7. Okay, and then the question would be, from our original equation, we had x plus y plus z equals negative 6, right? Let's try another equation. So x plus 2y plus 2z equals 11. We said x was negative 23. We said y was 17 minus 2 over 7. And we said z was 2 over 7. So negative 23 plus 31 minus 4 over 7 plus 4 over 7 equals 11. These cancel. 31 minus 23 is not 11, right? It's 12. Or it's 9. Wait, 31 minus 23.
Wait,
Questioning everything. 8. So these are not equal. Which makes sense. So let's see if I can catch the mistake. It must have been earlier. R2 minus R1 is 0. Sorry, make sure I'm following. So 1 minus 1 is 0. 2 minus 1 is 1. 2 minus 1 is 1. And 11 minus negative 6 is 17. That looks right. 2 minus 2 times 1 is 0. 3 minus 2 times 1 is 1. Negative 4 minus 2 times 1 is negative 6. 15 minus 2 times negative 12, negative 6, is 15. One minus 1 is 0. Negative 6 minus 1 is negative 7. 15 minus 17 is negative 2. Let me make sure. Oh my god. Oh no. Can you imagine if maybe I wrote it down. 1, 1, 1. This is positive 6. This is it.
So I mean, we did the work right.
We did the work right. We wrote down the question wrong.
We hit the right idea.
All right. Let's do one more of something else. Okay. And then. All right. Alright, here we go. One more. Maybe you can do this one, like, without my help. So 2x plus 3y minus 7 sine of z equals 7. Right? 2x plus 3y minus z equals 7.
Okay.
X minus 4y plus 2z equals negative 3. 3x plus y plus 4z equals 12.
Okay.
I wrote it down here. I'm going to make it a little smaller. Oh gosh, alright, this is where you can go wrong. Shrink it. Alright. Alright. So let's start by writing the augmented matrix. So what's that?
First row is going to be 2, 3, negative 1, 7.
Yes. Hold on.
And then we're going to have
Yep.
1, negative 4, 2, negative 3.
Mm-hmm.
Then we're going to have 3, 1, 4, 12.
Yep. Oh gosh. Alright. So, I'll give you a hint that probably the best thing to do here is first to switch rows.
Okay.
So which row do you think we would want to put first?
I'd say row 2 should probably switch with row 1, right?
Mm-hmm. So we're going to do R1, swap with R2. Okay. Could rewrite this as 1, -4, 2, -3, 2, 3, -1, 7, 3, 1, 4, 12. Okay, cool. What's next?
-3. So we probably want to turn that 2 into a 0, right?
Yep.
So we want to subtract.
How do we make the first one 0? Subtract what?
The first digit in R2. Like, how do we make that 2 into a 0?
Yeah. Well, we need to subtract how much from 2 to get 0.
Yeah,
right?
2.
Yeah. So if we're gonna subtract which row?
I suppose we multiply row 1 by 2 or
Yes.
something. Yeah.
That's right. Yep. Alright. So the first is 0, then what?
3 minus -4 times 2.
Yes.
So we'd have 11, right?
Looks good to me. Okay.
-1 minus 2 times 2. So we'd have -5. 7 minus -3 times 2. So we'd have 13.
Okay.
Cool.
And this is 3, 1, 4, 12. Cool. Alright.
Sweet.
What's next?
So remind me, would we want to pursue the zeros in row 3, or would we
I
want to?
think so. Yeah, I think that's the best bet.
Okay. So I mean, in that case, then we're probably multiplying row 1 by 3, right? And then subtracting it from row 3.
That's right.
Cool. Yeah. So we'd have 0. 13.
Alright, I just needed to write
Yeah.
everything out first. So 1 minus 3 times -4 would be, yeah, 13. Sounds right to me.
4 minus 6, we'd have -2.
Sounds right.
And then 12 minus -9, so we'd have 21.
Where'd you get? Oh, 3 times -3. Okay. Okay.
Cool, cool.
Cool.
All right. Do we want to turn that that 13 into a 0, right?
Yeah, this seems tough.
Yeah. Like we need to find like the lowest common multiple of like 13 and 4. Like I don't know.
Yeah, let me just check to make sure that it's correct. Oh, okay, yeah, it's it gave us one with weird numbers, but you're doing it right. So keep going.
We're just gonna have to up the scale, right?
Yeah, it's just gonna be like fractions.
Gotcha.
Yeah. So I think yeah, this is a tough one because it's why don't you just like talk me through what you would do next?
I mean, well, we want to turn that 13 into a 0. So I mean, I don't know. Like I was saying, like maybe find like the lowest common multiple. That both 13 and I don't know. I don't know. Would we do it with row 1 or 2?
You would do it with row 2.
Okay.
And you would just do so 11, it'd be like 13 over 11. So the way I get 13 from 11 is to multiply it by 13 over 11, right? Like if I have 11 times something equals 13, I gotta multiply that by 13 over 11. So this is what you would do.
Sure.
Yeah, so this is weird, but it should work. And then you'd have 0, 0, and then you'd have to do some weird math here.
Like -2 minus negative 13 over 11 times 2. Or sorry, negative 5. Sorry.
That's right.
Whatever that is.
Is
Okay. And then what?
then we have to do the last one, right? So
yeah, I mean 21 minus -3 times negative 13 over 11.
That's right. Okay, so just to check our work, I'm not going to do all the math, but we're going to end up with, 43 over 11 equals negative z equals negative 147 over 11. So z equals 17 over 43 times negative 147 over 11, which seems wacky, but I guess this is the problem with ChatGPT. 147 times 17 divided by 43 divided by 11. And what did ChatGPT say? Probably did something wrong. Alright. I think it'd probably be best to end the recording.
Yeah.
Because spent a lot of time. And I think for next time, what I'll do is I'll have better problems prepared.
That's fine. Yeah.
Alright, cool. Alright, well thanks, Cavan. I'm going to end the recording now.
Thanks, Matt.